Hello. So at this stage, I hope you have understood the concept of the likelihood ratio test that is testing the hypothesis that two models are equivalent, an unrestricted model and a restricted model. But in order to illustrate this, we will look more carefully into concrete applications of this test to see what we can get from a modeling perspective from a likelihood ratio test. The first application of the likelihood ratio test is benchmarking. The motivation is that there is no universal goodness of fit measure for a choice model. Therefore, the only way we have to check the quality of a model is by comparing it to another one. And in the context of benchmarking, the other one is a very simple model that is used as a base case. So in our setup, the unrestricted model is our model that we would like to test with the specifications that we have provided. This one. And the restricted model would be a model with equal probability. So a model that basically assigns 0 to all deterministic part of the utility and say that the choice which is made is purely random. It means that people, before they make a choice, they throw a coin if they have 2 alternatives, or they throw a die if they have 6 alternatives, and so on. So in this case, the restricted model is obtained from the unrestricted model by imposing the restrictions that all parameters are equal to 0. Okay, so this is the context where we would like to apply the likelihood ratio test. So we compare the log likelihood, the final log likelihood of both models. So on the left, you have the value that you have estimated from your data. You obtain the final log likelihood of your model. And on the right, you have the equal probability model. So for each observation, the model is predicting 1 divided by Gn as a probability for choice because it's equal probability. So you can calculate the log likelihood of this model by calculating minus log of Jn for each individual and to sum up over the sample. So the theory of the likelihood ratio test tells us that the statistic, which is minus 2 times L0 minus L beta hat, is distributed as a chi-square, and the number of degrees of freedom is the difference between the number of parameters of the two models. Well, the restricted model has 0 parameter here. There is no parameter. And the unrestricted model has k parameters. So therefore, it's a chi-square with k degrees of freedom. So comparing a model towards an equal probability model, most of the time is not really useful because the equal probability model is usually predicting so badly the choice that it's really easy to do better. So we would like to revisit the concept of benchmarking and say, can we do something better? Can we use as a benchmark a model which is slightly better than the null parameter model? And the idea is to develop a model which contains only alternative specific constants. So again, on the left, you have the model that you would like to test. This is your model. And on the right, you have a model where the v, the deterministic part of the utility function, contains only alternative specific constants. Now, in the context of the likelihood ratio test, you have an unrestricted model and a restricted model. The restrictions are that all coefficients except the constants are constrained to be 0. In order to apply the test, we need to calculate the final log likelihood of these two models. So for our model, this is the result of the estimation. And for the restricted model, a model which contains only the constants will reproduce the market shares in the sample. So the probability for alternative I will be the proportion of people choosing alternative I in the sample. So therefore, the log likelihood of this model that we denote by LC is calculated by this formula. And now we can calculate the statistic, minus 2 log of C minus log of beta hat. It is distributed as a chi-square with d degrees of freedom. And again, the number of degrees of freedom is the difference between the number of parameters in the unrestricted model, which is k, and the number of parameters in the restricted model, which is j minus 1, because j is the number of alternatives, but we had to normalize one of the alternative specific constant to 0, so we have j minus 1 parameters. So the number of degrees of freedom is k minus j plus 1. So actually, when you use estimation software for discrete choice, these two statistics are usually reported. So this is an example of the output of the BioGym software, where you have the summary statistics, where the number of observations reported, the L0, so the value of the likelihood for the null model, where equal probability model, LC, which is the value of the log likelihood for the constant only model. Of course, the final log likelihood is reported, and sometimes the test itself is calculated, so the likelihood ratio test, so that you can immediately apply the test by looking at these values. Another typical application of the likelihood ratio test is to test if a variable is generic or specific. So if you remember, we call a variable generic if it impacts the utility of all alternatives in the same way. This is the model on the right here, the generic model. So in this case, we have several alternatives, and the variable x and k is impacting all the utilities in the same way, in the sense that the coefficient is the same. But we can also have an alternative specification. In this case, the parameter, the coefficient of the variable will be different across alternatives. So the unrestricted model is the alternative specification. The restricted model is the generic specification. And the restriction in this case is that all these betas are actually equal in reality. So what do? Well, we first estimate the unrestricted model, the one with alternative specific betas, and we calculate the log likelihood function. Then we write the restricted model, the one where one parameter is used for all alternatives, the variable is generic, and we calculate the final log likelihood. And then we can apply the test, okay, and the test is again a chi-square with d degrees of freedom, where d is the difference between the number of parameters of this model and this model. So typically, if you have one set, or if you test only one variable, this model will have j betas, when the next one will have only one. So if you have only one variable that you want to test, the degrees of freedom will be j minus 1. We have emphasized several times in this course that it is very important to capture heterogeneity of taste. So people are different, we have different behavior, they make different types of choice. So this is something we would like also to be able to test. Is it the case that people have different taste for travel time, for cost, for whatever? And we can use a likelihood ratio test to do that. The way to do it is to take the population, to segment it, so to organize the population into groups, let's say G groups, and the size of each group is NG. So the size of group G is NG. Then we write a specification of the model. The same specification is considered for each group, but a different set of parameters is estimated for each group separately. And then the idea is that the values that we obtain by estimating the model in each different group separately, how different is it from the set of parameters that we would obtain by estimating the same model on the entire sample? So this is the idea. So let's consider this rectangle as our sample, and we divide the sample into 4 groups. So we have group 1 that contains N1 individual, group 2 with N2 individual, group 3, N3 individual, and group 4. So the total number of individuals in the sample is N. So in order to calculate the value of the parameters and the model for this segmented sample, we first estimate the model only using the first set of data, and we obtain a final log likelihood. Then we do the same for the second one, we obtain the second log likelihood, and so on. The third log likelihood, and the fourth. So this is easy to do. It's exactly the same model which is estimated, but on different data sets, group 1, group 2, group 3, group 4. Now, when you put all these together, the final log likelihood of these models, where a different set of parameters is associated with each group, well, the total log likelihood is simply the sum over all log likelihood that you have calculated in each group. So this is the unrestricted model. Now, the restricted model is a model with generic coefficient, where there is no segmentation, where the same model, the model is applied to the entire sample, and there is only one set of parameters. So in this case, the restriction is that these parameters are equal across groups. That's the restricted model. And so in this case, you can apply the log likelihood ratio test. As we saw before, the log likelihood of the unrestricted model is the sum across groups of the log likelihood that was obtained by estimating the model on each separate group. And this is simply the log likelihood of the restricted model, where there is only one group. And you can calculate again the t-statistic. And the number of degrees of freedom now is what? Is the total number of parameters in the unrestricted model, which is g times k, minus the number of parameters in the restricted model, which is k. So the degrees of freedom in this case is g minus 1, where g is the number of groups, times k, which is the number of parameters in the model. This test is very important because it's extremely easy to apply. Okay, you just apply the same model specification on different subset of your sample and do a quick calculation for the likelihood ratio test. And it tells you immediately if it is worth investigating possible heterogeneity of test in the population. Because if the test rejects your hypothesis, so it means that the restricted model is good, then you can actually forget about segmentation for this variable. So I advise you to use this test a lot before you start investigating specific heterogeneity in the sample. In the previous week, we have seen the possibility to provide nonlinear specifications of the utility function. And we have investigated several tools that can do that. But is it really worth it? So again, like we did for segmentation, maybe it's worth testing first if the linear model is good or not. And to do this, one way would be to use a power series. The good thing with power series is that any nonlinear function can be approximated as close as you want by a polynomial. Therefore, if the true utility function is indeed nonlinear, the specification using the power series will capture that. So the idea here is to say, on the one hand, the unrestricted model is defined as a power series of the variable. So for example, you have here the sum for L equals 1 to capital L. So capital L will be the maximum degree that we would like to consider. And here we have the variable raised to the L. And it's also divided by a reference value in order to avoid numerical issues that are associated with large number being raised to a power. So this is the unrestricted model, the nonlinear one, and the restricted model would be the associated linear specification, where the variable xi and k is involved in a linear way in the utility function. So actually here the restrictions are simple. It means that in the power series specification, all coefficients of the nonlinear terms are equal to 0. So beta 1, 2, beta 1, 3, all the way to beta 1, L. So this is an example. So suppose that we have the relationship between the variable x1k and vin, the utility. What we do is that we compare the linear specification, which is in red here, with a nonlinear specification which is flexible, which is the power series, which is in blue here. And we will be able to see immediately if we indeed have a nonlinearity in the data or not. So the log likelihood ratio test will be applied exactly as we saw from the beginning. So we estimate the unrestricted model, the one with the power series. This is the one on the left. Then we estimate the restricted model, the linear specification, which is the one on the right. And the statistic is always the same, -2 times the difference of the log likelihood. It's distributed as a chi-square with d degrees of freedom, where d is the number of power series terms that we have included, -1 because we keep the linear term. These power series are actually very flexible, so it's very tempted to use them a lot. But although it's very useful to use them for testing, as we saw before, they are usually not very meaningful in terms of behavior. What does it mean that people involve the travel time raised to the power 4? I don't know. And also, the flexibility of these models comes with the danger of overfitting, meaning that you may actually fit the noise in the data and not the actual behavior. So polynomials are most of the time not appropriate when you want to do extrapolation. I mean, polynomials oscillate a lot, and this is something which is dangerous. So I recommend to use these polynomials for testing, but use overspecification for the final specification of your model. And actually, these specifications that we have seen, like the piecewise linear and the Pox-Cox transforms, could also be used for testing if you want. The likelihood ratio test is very powerful. First, it's simple to calculate, and then it can be applied for many types of specification testing. So this is really advisable to use it a lot in many contexts, and we have seen several in this video. But you have to keep in mind that it can be applied only when the restricted model is obtained using linear restrictions from the unrestricted models. It was the case in all the examples that we have seen in this video, but it's not always the case in practice. And we will see later on other tests that can be used when this is not verified, when the restrictions are not linear.